Welcome. You guys in the back, behind the bar, and maybe even the top row over on that side, you might be a little too far away for the clickers to be picked up. I noticed it in some of my classes last semester. So if you notice that you're not getting like bonus points or clicks, it's possibly because of that. This is a little hot. Bring this down. Okay. All right. Here's our outline. We're going to have written homework due tomorrow, and everybody is going to turn in their paper. And I'll tell you exactly how to do that first thing tomorrow. The paper that you're going to turn it in on is a PDF, and I will put it inside web courses right after lecture today. Okay, so we'll finish at 4:50, and at 4:51 or so, you'll be able to download it, read the problem, and then start working on it. And then when you turn it in, you'll turn it in. I mean, you can do as much scratch work and graph paper work as you want, but I want a really sharp-looking communication to me on that handout that you hand in tomorrow. All right? So now in lecture, when you see me up here on the document cam, which we'll do a little more today, I'm really working fast, and I'm going to try to slow down a little bit today. But I want you to just, and some of you are going to be working up to the last minute, 2:59 p.m. tomorrow. That's all right. But try to do, it's a fairly simple problem and actually easier than the one that we're going to do on the document cam today. So hopefully you'll be able to do a good job on it. A little bit of trig, a little bit of Newton's second law, putting together F net, a net force. So that'll be good. Anyways, I want to talk about Wiley plus. Get your clickers ready. We're going to do clicking in a minute. But before we do that, yesterday was like technology fiasco day at UCF. And not only was the Wiley Plus website not cooperating, but some of my other software was not cooperating. And I didn't leave here until about 8 o'clock. And then when I got home, I found out that you guys, your homework wasn't even visible. And so I figured that out about 9 o'clock last night. So anyway, but we'll one of the things I notice is that Wiley Plus, it works differently. It's and I put a little discussion post about it there. You can see the green and the purple. You go through each question and you get 4 tries at the question. And if you go to the next question, can you go backwards? Back to the question. So you can go backwards and forward, I guess, but you just get one shot. And when you're done, when you close that window, that's it. Versus if I do the exact same questions word for word, multiple choice in web courses, you do each question, then you submit the entire thing. And then if you don't like your answer, you go and do it again. And I'm not really, sure which I like better. I'd be happy to entertain your opinions about which one that you like. Although the academic integrity quiz is in Canvas. And the Wiley homeworks that we have had are, of course, in Wiley Plus. The other thing I noticed is that if in a web courses assignment, normally I set it to 45 minutes. Most of the time, that's plenty of time to work on it and do a little study and then work on another problem and then a little more study and maybe get, your homework done and then submit it and then see what you got and, go back and study some more and then give it another shot. That doesn't work that way in Wiley Plus. So I'm thinking that I might make the time limits like 2 hours on the Wiley Plus assignments, just so that you can, they have nice study tips in there and stuff, but if you actually want to go and read the book or listen to my lecture again, it might behoove you to have a little more time with that. So, and in addition, for students that have accommodations for extra time, I haven't figured out how that's going to work yet either. Also, does anybody have any questions for me before I proceed to the next topic? I asked somebody. Okay, go ahead.
So right now you just have homework in Wiley Plus?
Right now you have homework in Wiley Plus, and then the academic integrity quiz. I haven't looked to see if everybody... I told somebody to ask me in lecture. I sent a message. I guess the student is too shy to ask. The student asked me, Dr. B, I really didn't get a chance to do this because it didn't come open and then it didn't work. And so just so that I let everybody know, I'm thinking about totally downgrading these first 2 fiasco assignments until we get Wiley Plus really rolling, which probably will be the next Wiley Plus assignment, which will be tomorrow night. Tonight you don't have Wiley Plus. Tomorrow night you'll have Wiley Plus, and it'll be a fairly good-sized one over the weekend in Chapter 18, and maybe a little bit of Chapter 19 preview. And hopefully we'll have everything set to where you can do it right after class, and you'll have plenty of time to do it, and stuff like that, so that people won't get all flustered and flabbergasted and whatnot. So if you feel like you biffed it, like I know a few of you said, Dr. B, I don't even have a grade. I did it, and I don't even have a grade. And the reason is because I hate to say it, but I found out yesterday that I found out this morning that when I tried to change the settings in the Bernoulli concepts so that you would have more time or more attempts or something like that, I inadvertently destroyed all the scores of people that had already done it. So we're gonna. I'll square you away. Don't worry about that. I'll square you. Anyways, we'll get it working good. Okay, I posted another bonus point for early registration. So if you registered by about 5:20 yesterday, you got a bonus point, and you were here to click, then you got a bonus point. So I'll synchronize the roster for, and you know what? 180 of you are registered, so that's great. There's only about 40 that are, doing something else. But if you registered after about 5:20 last night, you'll be, and you click today, which we're going to do in a second, you'll get a bonus point for today. And then another bonus point for Friday. And then Monday we start the regular participation points. So right now, all you got to do is have your clicker if you can. No skin off your nose if you don't. But Monday, yeah, skin off your nose if you don't. But hopefully, you'll have everything squared away. Any questions about the clicking situation? Yes?
It's not about the clicker, but with the exams, will we be able to open our assignments for studying purposes?
Yeah, the student, are you the one that I asked about that? I think somebody asked me. It was you? Okay. Same question. Great minds think alike. The question was, will the homeworks be viewable again so that we can study for exams? And the answer is Ooh, if it was a web courses, I'd say, oh yeah, takes about 2 seconds. For Wiley Plus, I'll give a conditional, definite maybe. If in other words, I will try to do it, but I'm not sure if it'll, discombobulate everything. But I'll, because I don't want to destroy anybody's grades again. So, but I understand what you want, and I'll try to get that for you. If it was a web courses thing, and we'll probably have a few in web courses of my homemade problems, and you'll be able to get those viewable and hopefully the Wiley Plus as well. Another question? Yes? How should you study? Good question. It's a little early, but it's that's half a semester away. Anyways, the most important 2 things you can do to prepare for my exams are study with another human being and talk things over. Like the saying, iron sharpens iron. And just are you listening? Just the fact of talking with your study partner, whoever it is, like somebody you sit with in class. What's that? Well, you may find that you're not equally confused, and that, well, now you're being disrespectful, and you're trying to, but what I want you to do is study with a friend if you can, because you want to be able to think. And to talk with somebody about a problem will force you to think. The second thing I want you to focus on is that lectures are priority. There's a million things in this text that I could talk about, on fluids. I mean, we could spend a month talking about that one chapter if we wanted to. So every day I have to make a decision. Okay, what should I was just doing it a few hours ago, trying to figure out what should I put in today's lecture. I have to make a decision every day, every lecture, what is important and important enough to include in lecture and what's not. And then I talk about that important stuff in lecture. And then an examination is basically me interrogating your mind with questions, scantrons and calculations and stuff, to see if you understand the important stuff. All right? And so when you're going through your notes, your lecture notes are your study guide. Think of it that way. And what we do in lecture is the most important. Secondary importance are the clicker and the homework questions. Okay? And then third level of importance is everything else in the textbook that supports lecture. Okay? So in other words, today I'm going to be talking about the Coulomb force law, but I'm not going to talk about every single thing in chapter 18, subsection 1 through subsection 5. Okay? But if you read through there and you say, oh yeah, he did talk something about this in lecture for a second, and it'll help you solidify that. So those are my 2 suggestions, the priority. And 3, I guess, don't be so nervous about the test. Try to study hard, but don't study all night and we have exams we're going to have exams basically at 4 o'clock, so hopefully you'll have had, a good night's sleep beforehand and plenty of study time before the test, but don't You know, everybody's going to be extra nervous, especially with the first exam, because you've never had an exam from me. But after the second exam, you say, okay, I know what Dr. B's style is now, so I know how to study. So you're going to feel better about that after the first midterm, okay? So in the first midterm, try not to stress too much. But remember to think, studying with a study partner of some kind or a study group, or in discussions. You know, discussions is the same. That's like your virtual study group. You know, ask a question or respond to somebody else's question about, you know, number 14 on page 293 or whatever it happens to be. And then that's discussion, and that'll help you as well. Okay? And so that's my advice. You know, so study everything with those priorities in mind. Question? No, no formula sheet. I'll give you the formulas that you'll need. Formula sheets are worthless. You know, I've seen students, for instance, we just did calculations with pressure the other day, right? The letter P is the symbol. I've seen students make like extremely like negative 17-point font formulas, you know, just so it looks like you can't even read it, you know, and they have a momentum formula or several momentum formulas, and they use the letter P. And then they have pressure formulas, and that uses the letter P. And maybe they have, if it's a quantum class, P for probability density, and that uses the letter P. And I have seen students use pressure formulas for momentum problems, and vice versa. And that's because it's like a security blanket. Now, what I normally do on exams, and you know, this is just a preview. Usually I mention this the day before, but it's okay to mention it now. On exams, what I do is the first 2 or 3 questions, 3 or 4 questions are matching. And so I'll give you, you know, like 3 or 4 formulas, and then a bunch of concepts, and then you match the concept or like the name of the formula to the formula itself. And so that'll be the equivalent of a formula sheet, and only the formulas that you need, okay? And maybe 1 or 2 extra formulas just to, you know, to round it off. So you won't have to worry about formula sheets, okay? And that goes back to what I've said before. Memorization is nice in other classes, but in this one, I give you the formulas. I want you to think with the formulas, with the sentences that I give you in the problems. That's going to be the challenge. You know, and you know, Albert Einstein had a famous saying. He said, if we knew what we were doing, it would not be called research. And so this is Einstein, right? Like the second smartest guy that ever lived. And the same things that you struggle with, everybody has struggled with. And they're just, you know, Einstein was struggling with stuff. But everybody struggles with it. And so, and the thinking is the hard part, not the formulas. I mean, you can hire a dozen engineering majors to help you memorize formulas and stuff, and that's not going to help you much, you know. So, all right, let's keep going. I put a new page in web courses for you. It's called the homework list. It's basically, a list of the homework assignments. And I'll have some written problem files over there for you as well. And so what I try to do is link information in more than one place. So that if you miss it in one area, you might see it in a different area. Okay, so it's gonna be in modules as well, and so you might like to just go click. And there's a link to the homework page right next to the photo, or right next to the portrait of Michael Faraday. Question? How many questions? I'll tell you that next week, next Tuesday. I mean, we don't have class Wednesday, so Tuesday I'll tell you more about the exam. All right. Question about that? Did you have a question with the bluish pant? Yeah. No. Okay. I saw you going like this. Okay. I'd like to ask a question, but That's all right. Okay, the talking PDFs that I recorded at the document camera with my smart pen yesterday, they are in another page, talking PDF page. This is what it looks like. And there's a couple links one to a website, one to the software that you can download to your desktop or your laptop and view it. And there's a website where you can view it just by uploading it into the website. It works both of them work really nice. Raise your hand if you've already tried that. Anybody? You have? Did it work okay? Yeah, okay. Anybody else? Okay. And it's a good study tool. I mean, you can just print it out and you'll have my notes, basically what's in my notebook. But if you play it, you'll hear my narration and stuff. So it works nicely. All right, onwards to chapter 18, electrostatic force and field. We're going to go up to section 5 today. Let's do some, whoops, this one got a little discombobulated. Let's do a clicker question. And this is going to be a multiple choice. So let me get a multiple choice question here. And again, let me show you this. This is a little warning that I get. It says, press and hold your power button down for 2 seconds, and then press DD, and you'll be on my frequency. That might be another thing that, you might not have been on the right frequency. Anyway, so let me switch back to the laptop. I got 2 cursors I have to do here. Okay, so that question is going. Here's your question. The room is quiet. The students are thinking. Go ahead and make a decision. Oh man, this thing is all blooped up. I inadvertently. Okay, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, 187 people answered that one. Let me pause the podcast. Okay, let me check to see what you guys voted for here first. Nice. Good. Most of you got that one correct. Now I want you to hit the refresh key, if you will, on your, because now you're going to answer a question by typing in some words, some letters. Okay, now as soon as I start this new question, it's going to be a short answer. Oh boy, hold on. Timeout. Okay, here we go. Here's your question. Same array. Different question. Now this one, you should have the up and down arrow key to select letters. So select a letter, like Y if the answer is yes. And then hit the right arrow key and then go up and down to find the letter E. Or if you don't think the answer is yes, type in a word. You have 14 character limit, I think. Hit the okay. Hit refresh one more time. Now try it. Okay. Hear that? Listen to the clicking. Don't type in the word no. Type in, what you think is you'd need, and then hit the send key. I see a couple of you putting in no. Don't. If you want to say yes, say that. That's okay. But don't type in no. I see somebody typed in a word, 4-letter word. Another one, okay. Aha! You guys are thinking, good. Boop, somebody forgot a couple letters. They're trying to spell a word that, I'm not going to give it away. Uh-huh. Interesting. No, don't type your name. It is a practice question, but I mean, it's also a serious question. Because I want you to think about this, this question. Do you have all you need? Or do you need more? When you're writing a problem solution, you've got to think about that. Do I have what I need to make a calculation, or do I need more? Huh? I don't know. What do you think? See, this is good, talking and stuff. You guys, when you're doing a question like this, go ahead and talk and visit with your neighbors. I encourage it. Not on a test, but in lecture, yes. What's that? You did? Okay, good. Yeah, I can see. Okay, 1 minute to type in your number, and don't forget to hit the send key. If you type in yes, or if you type in something else, hit the send key. Otherwise, you got it? $20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Sweet. 188 students just answered. Let's take a look. In fact, let me make this gigantic. Let's switch over here. Now, some of the answers here, 24, 2. I don't know about that, but and it's not being graded, but acceleration. Do you need the acceleration to calculate the force? Well, yeah, if you know MA. I mean, if you know M and then you know A, yeah, you can get it because MA. Charge? Charge is implied by it's an electron and a proton, or 2 protons. Okay, so you could look those up. It's not a mystery. Let's look further down the list here, see if I can do this. This thing burns my grits. You can't. Charges. See, how do you get this thing to go down? I don't. Oh, here we go. Okay. Charges and radii. Constants. Ah, that's an interesting question. The constant, yeah, Coulomb's constant. And I'm guessing that Coulomb's is... I'll just take that as somebody attempting to spell Coulomb. And the one above it, charges and radii. Coulomb's, they're spelled... Don't laugh. It's... look, you guys are I don't laugh at that. I just see, because look, I know how it's tough to get the letters, especially as you guys will find out, the decimal point is like, you need a microscope to see it. Distance, yeah, that's basically what you need. That's the basic. And I'm glad to see, but notice distance between, that's good. Disty. You guys are getting some, we're not looking at this for kicks. And I'm not looking at it to make fun of anybody, really. But you know what I am looking at is that, do you see how many, just one person voted for it? And how many have I said are correct? A lot of them. So this is the kind of a question that you can type in the correct answer and be different from everybody else and still be correct. And that is something I love about this kind of question. Because, you think about it, a multiple choice or a true false, I write the question and the answers, and you just got to, and I control everything. But this, you write the correct answer. And we're going to be doing even fancier questions than this. Grams, yeah. Info, boom, yeah, kind of. Magnetic field, no. Magnitude, mass electron, missing L. I wonder what that means. And I'm not going to ask you to explain it. Molar mass, that's chemistry class. No. Need coulombs, need distance. Yeah, this is good. Yeah, you need more. Net newtons. Okay, this guy's a wise guy because that's the answer. If you want to know the net force, just give me the net newtons then. Anyway, so this is just a practice question. But on exams, I've mentioned that I'm going to want you to bring your clicker, and on an exam, you will have a deluxe question of this kind. Probably not the final, but definitely the midterms, in which you write in, you think it over, and you write in an answer that is correct. All right, and I'll be looking at it, and most of them I won't be laughing at, although I didn't see a very popular one in here. This is all alphabetic. See right in here, there's usually somebody that says IDK. But, all right, let's do another question concerning the electric field. And I got to get this clicker business. So hit the refresh key again. Now we're going to do a survey question. And you're going to be typing in answers again. But this one is a survey. And so the way that I take this one, let me give you the question. All right, here's your question. Okay, and this is a survey. And on a survey, every answer is graded correct, although there is a correct answer. Okay, so this is kind of a technical question that I don't expect you to know the answer. I just want to kind of see where you stand. So let me start the question. Okay, you should be able to start, and now all you got to do is type in A, B, and C on this one, and then hit the send key. A, B, C, D, or E. But so technically this is a short answer question like the previous one. but it's a survey, so I'm able to grade all of it for you. And definitely talk things over. If you've done any reading in the chapter, you'll maybe know the answer. Do you know the answer? Yeah, you read. Yeah, good. Are you guys operating clickers back there in the back row? Are you getting checks? Check marks? Okay. All right. You got checks? Okay, good. I don't know. It's 30 seconds to vote. $20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. And if you don't get your answer in on time, you're going to find, my participation is not 100%. And you want to get as many answers in as you can. All right. So let's see what you guys voted for. A lot of you voted for A. Huh. All right. I see some people screwing around in there. This is actually the correct answer. You might want to make a note of it. Yeah, the mass decrease is if the net electric charge is positive. And the reason for that, when something normal size other than an atom, and even atoms really, if it acquires charges because electrons have moved into it, making it a net negative, or they've moved out of it, making a net positive. So if it's positive, it's lost a few electrons. So technically that means its mass is a little bit less. So let's keep going. And we're going to get down to brass tacks. And I'm going to give you some comments now from chapter 18. And they begin the chapter talking about atoms, electrons, and protons. And to me, that is actually the modern view of it. But in the early days of Michael Faraday and Benjamin Franklin and Ampere and all those guys, they made huge discoveries. The whole idea of positive and negative charge, that's Benjamin Franklin. And he's the one that made the decision what's positive and what's negative, and we still go by his. So that's why electrons are considered negative. He didn't know about electrons, but he knew that there were two different kinds, and he called one positive and one negative. Michael Faraday, he discovered electromagnetic induction and a whole lot of other stuff. And all this electricity that we have is not from batteries somewhere. It's from a generator somewhere, at a power plant that is operating on the principle of electromagnetic induction. Now, atoms and molecules were verified in the early part of the 1900s. And so I mention this just to say that in knowledge, it's a good idea to be humble about what you know, because you're standing on the shoulders of giants. Everybody, we're all following Professor Galileo. And Sir Isaac Newton was standing on his shoulders, and everybody else is standing on the shoulders of a bunch of other people, including Franklin, Faraday, and all those guys. Now, as we see, as we shall see in later chapters, there are subatomic particles that are the particles that make up quarks, that make up protons and neutrons. They're called quarks, and they come in a whole set of different flavors. Okay? So positive and negative electric charge, the Coulomb interaction, yeah, that's nice, but the force that holds protons together is completely different force and has several different flavors of, charge. Now, they also make a mention about charge being quantized, and that was an experimental discovery. They kind of go about it backwards in the textbook. So I just want to make sure that you have a little bit of guidance on those concepts. Now, the electromagnetic interaction, here's what we were talking about in the last clicker question. A body, and this is a quote from page 482. And notice there that in parentheses I have page 482. And I will try to put little keys in there. I don't always put them in, but I'll try to put a cue as to, where in the textbook, it is. And this is a pull quote. A body that gains electrons acquires an excess of negative charge. Quote from page 482. The body that loses electrons has an excess of positive charge. And that's why something that's positive is a little bit less mass, because it's lost its electrons. And now here's a couple comments to accompany that. The charge accumulates in physical objects for the most part by the motion of the electrons into or out of an object. Now the exception to that is someplace like the surface of the sun, where the gas is so hot that the atoms are completely ionized into what we call a plasma. And it's just a bunch of nuclei, hydrogen nuclei, and electrons floating around, and a bunch of helium in there. It's a maelstrom. But for most everyday things, and even for atoms and molecules, an ion. If you've had chemistry class, which I'm sure you biomedical types have had out the wazoo, an ion is something that's either lost or gained an electron. You don't usually ionize something because you've tossed out a proton. That would be a nuclear reaction, by the way. And yeah, you can do it. The sun does it all the time. It manufactures new nuclei, changing the charge of the nucleus, changing the mass of the nucleus, but usually it's the electrons that do the charge rearrangement, and that's because they're smaller. The mass of an electron is 2,000 times smaller than the mass of a proton. They have the same electric charge. Electron is negative of what the proton has. But the proton has way more kilograms of mass. It's still pretty tiny, but it's tiny, but it's 2,000 times bigger than the electron mass. And that's why the electrons are the ones that do the ionizing and the charging, because they're easier to move. So F equals ma is way easier for electrons. Now, when you're ionizing something or charging something, you're not destroying or creating electric charge. You're just rearranging it. So you're stripping, so if you make something net positive, basically you've got some positive ions. You've stripped some electrons out of a few of the atoms, usually near the surface of it. Okay? But those electrons haven't disappeared into space. They're going to accumulate somewhere else. Or they might, if you're near, something that's connected to the building, it'll go through the ground and into the earth, as the textbook explains about grounding. So things are not created or destroyed; they're merely rearranged. The law that we have for that is this one: the law of conservation of charge. And we will, and it's in chapter 18. You can read about it there. And we actually will be applying that in a very practical sense in the chapters on circuits. Because the circuit, electrons move around in the circuit, and unless you get an arc from the circuit, out to the ground or something, like a short circuit, then the electrons, they don't go anywhere. They just, move around in the circuit. Did you know that electrons, like when I turn on the lights here, the electrons are going a few millimeters per second. It's not like it seems like it's instant, the speed of light, but it's not. What communicates is the fact that the electrons move a few meters per, and all the electric field is set up at the speed of light, and the electric field sets up in the wire, and then that means all of the electrons that are free to move march instant or pretty close to instantly. But if you actually tracked a single electron, yeah, it's just a few millimeters per second. You can figure it out. It's not too hard to do. I might do that in one of the later chapters. Okay, polarization and conduction. Now, here's another topic that's pretty important. Polarization. And I really love this diagram. This is figure 18.4. Okay, and they talk about something called electric ink. And basically those two blobs are polarized. It describes it describes a little micro droplet in which there are little tiny balls of white plastic, and I don't know how they make it, but the balls go to the bottom when the copper plate below is positive. They go to the top when it's negative, so they get repelled to the top. So that sphere, that little globule, is polarized, back and forth, right? Now, polarization means that you have an accumulation of negative in one part of your object and an accumulation of positive in another part of your object. So positive and negative, they spread out the way this one has. The ink is supposedly positive, and that is in the top on the first half of that diagram. And you can read about it in the textbook. Another thing is page 484. There's a very good description of electrical conduction. And it basically says that in a substance like a metal or even carbon, the metallic bonds are overloaded. In other words, they have more electrons than they need to bind into a metallic bond, into a metal. So some of the electrons that, they're not really needed for that bond, they're free to move around. Copper's got 2 valence electrons. Those are what they call the valence electrons. Okay, and in chemistry, the valence electrons are also involved with bonding molecules together. So it's not just conducting electricity, it's bonding molecules. It's also oxidation. Okay, so oxidation is the process of stealing and being stolen from. Sodium, one of the electrons of sodium being stolen by chlorine. The electronegativity of chlorine is so high that if there's a sodium nearby, it'll steal that electron. And then you got 2 ions, and guess what happens? They bond together as ions. And that's the stuff that we call NaCl, sodium chloride, which is kind of interesting. Sodium chloride. Sodium, did you know this? Maybe those of you that have chemistry class, you've probably had a chemistry prof tell about this. Sodium, metallic sodium, if you, so pure sodium, if you expose it to air in the lab, it'll blow up. The water vapor in the air in the lab, it'll blow up. And when I was in high school, our chemistry prof, Dr. Cooper, they had to evacuate the school because he was handling some sodium and he accidentally exposed it to air. And he was a tough old bird. He didn't end up in the hospital, but it blew him all the way on the other side of the lab. And they had to call the fire department, set off all these alarms, and we had to evacuate. So no school for the rest of that day. It was pretty sweet. But old Dr. Cooper, yeah, that's sodium, so it's pretty, and chlorine. So sodium's pretty dangerous, right? Chlorine. Do you know that chlorine is the first weapon of mass destruction? Chlorine gas. In World War I, they used it. The Germans figured out a chemical process to manufacture abundant chlorine gas very cheaply. I don't know, what the process is. And then they knew that it was toxic, so they started spread. The problem with that stuff is, when the wind shifts, it comes back on your own troops. So anyway. So two really dangerous substances, right? Sodium and chlorine. Separately, there's a lot of danger. But when they bond together, it's the salt of the earth, the stuff that you need. You have to have it. And in your body, so you biomedical guys, what is it, sodium ions that form ion pumps? Or what is it? Sodium potassium pump. Yeah, because you need potassium as well. So yeah, you got to have that stuff. Another comment, and this diagram is nice for that as well. This is figure 18.6. Ebonite, that's kind of a plastic, and if you rub it with cat fur or something, it'll charge up with negatives. And then if you touch it to a metal sphere, some of the negatives will go into the metal sphere because it's not. If the metal sphere is not initially uncharged, a few of the negatives will go in there. And then they'll redistribute themselves, they'll equilibrate, and that's the second part here, image B. The electrons they'll redistribute themselves strategically so that they're getting repulsion from their other free electrons that are, the conduction electrons. But if they're a little bit too close to one, they'll move away until everybody's at equilibrium. And that is why the charge accumulates usually on a conductor on the surface. And we will actually use that later in this chapter tomorrow when we study Gauss's law. Question?
Just to clarify the use of equilibrium and equilibrium here, is it just referring to like an even dispersion?
Dynamic equilibrium. And what that means is the force is F net is 0. So it kind of jiggles, they all jiggle around until everybody's, got equal forces from its neighbors, but they all balance out. Okay, so kind of a network, forms kind of a network, we think. But go ahead.
Does it mean that they'll be like evenly distributed? Or
Yeah, it means evenly distributed. So spatially they'll be, because they're all electrons, and so they'll all be the same average. And it's on average, because there's things jiggling around, but the average distance between the conduction electrons will be the same until it'll adjust itself until F net is equal to 0. Now, the exception to this is insulators. Okay, so stuff like rubber, plastic, wood, all different kinds of things that don't really conduct electricity. They've got electrons in there, but those molecules, when they bind together to form the substance, whatever it is, polypropylene, that's a big hydrocarbon molecule, they bond together. There's no conductions electrons that are easily moved. So you don't really see electrons moving from, one end of a piece of plastic to the other end. It's an insulator. It prevents the conduction of electrons. And there's a nice set of, you could read it. There's a nice description of insulators in there as well. And some nice diagrams around page, 480 something, figure 18.6 and so forth. Now, let's take a 5-minute break, and we'll come back and get down to the nitty-gritty of Coulomb's law. So 4:02. Okay, we're going to talk about Coulomb's law, which is the law of the electrical or electrostatic interaction, the Coulomb interaction, in chapter 18. Here's the basic spec. The formula is down below. That's the way the textbook. They use the absolute value bars around the charges. Q1 and Q2 represent the amount of charge in the two charged objects. Now, if they're oppositely charged, the top diagram, then you have attraction. So the two force vectors are toward each other. But if you have negative and negative, or positive and positive, that's image B. They point away from each other. That's repulsion. Okay, now everybody knows that. Likes repel, unlikes attract. The size of the, and I enjoin you, or I admonish you to read this section on Coulomb's law. It's pretty good. And they use this formula down here. The letter K is known as Coulomb's constant. And it is basically a conversion factor, or it was in the early days, when Coulomb developed this law in France. But it's actually has a lot more meaning than that. The whole idea of a point charge is something that they talk about. When the distance between the two objects is a lot larger than the average size or the average diameter of either object, then you can treat either object as a geometric point that has magnetic charge. And electrons are close. We don't know the actual diameter or radius of an electron. We've never been able to measure it. It's so small that it's almost as if it's a point charge. But it's a physical object. It has mass, so you can't really say that its radius is zero. I mean, that would be a black hole if that were the case. But mathematically, treating something as a point charge is pretty useful, and even though we don't actually observe it. But it's a pretty good approximation in a lot of systems. And they give you an example that's kind of outlandish that we'll talk about in a minute, where they calculate the interaction force. It's pretty ginormous. The other important thing is that it's a pairwise interaction. Now, when we get to the section on atoms and electrons, I'll show you something called a Feynman diagram, which is the quantum mechanical way of viewing electrons and photons. Photons are the quanta that mediate the electromagnetic interaction between electrons, positrons, protons, and everything else that has electrical charge. And the fact that it's a pairwise interaction, so point charge to point charge, is important. And it's a huge help because we can analyze an array of several charges by looking at separate pairs. So if you have three charges, and you care about, charge number 1 over here at the origin, and you have a charge up here, and then you have another charge up here, well, you analyze this pair, and then you figure out the net force on this guy. And then you analyze this pair up here, right here, and you figure out the net force on this guy. And then you just add them up, just like in Newton's second law. And we're going to do that in just a few minutes. The Coulomb constant, as I mentioned, it started out its life just like Newton's gravitational constant, G, capital G. A constant of proportionality, kind of like in the annoying conversion that you have to do in like 5th grade science class between, you remember this, Celsius to Fahrenheit? And you got to, I still don't, I still always have to look it up. You subtract 32 or you add 32, and then there's a fraction of 9/5 and 5/9. You remember that? So that 5/9 is a proportionality constant between Fahrenheits and Celsiuses, or Celsius. All right? And so K is something like that. Only, see, because here's the thing. The things that you actually measure are the charge and the distance. That's it. But Coulomb squared, that's the metric unit of charge. Coulombs squared in the numerator divided by square meters in the denominator, that's not a Newton. So you have to have some numerical factor that converts it to Newton, and we're going to use that in just a few minutes. Now, example 2, this is the one, oops, I went the wrong way, sorry. Okay, here's example 2, and I have a couple comments about this. Go ahead and read it. It's on, I don't know, page 490 or something, 480 something. They're using huge amounts of charge on this, and they admit it later down in paragraphs below there. 1 Coulomb, they have a 1 Coulomb and a negative 1 Coulomb charge separated, I think it is, separated by a kilometer. And then they're figuring out, in that example, how big is the force. And it's pretty big. It's a lot of newtons. All right? Now, the difficulty with this problem is a Coulomb of charge is an enormous amount of charge. If you have a wire in which 1 Coulomb of charge, that's roughly 10 to the 18 electrons, 1 Coulomb of charge goes through the wire per second, past a given point per second. That's 1 ampere of current, right? 1 Coulomb per second past a given point in the circuit is 1 ampere. Okay, that's the metric unit of current. 1 amp will kill you, dead, if you permit it to, flow through your body. So it's some serious juice. And if you go and look in the breaker box at your house or your apartment, you'll see amps in there. Like, a lot of times, the air conditioner will have like 2 breakers, and they're both like 35 amps or something like that, big, because the AC uses a lot of juice. And what else uses a lot of juice? The dishwasher, the washer and dryer. They'll have their own circuits, and those circuits are measured in amps, and that is a serious amount of electricity. All right? So that's just a comment about this particular example. Now, they also say that Coulomb's law has a form that is remarkably similar to Newton's law of gravitation. And there's an important distinction and an important similarity that I'd like to comment on. And you can see that I've highlighted it. And you know what? I need to give you guys the method for subscribing to my highlighters in Bookshelf, because it's pretty easy to do. Anyways, you can see I've highlighted it in yellow in Bookshelf. Similarity. They're both inverse R squared laws. Go ahead and write that down. Inverse R squared law. Newton's law of universal gravitation, G m1 m2 over R squared. Nice. That's an inverse R squared law. Coulomb's law, K Q1 times Q2 over R squared. Nice. Inverse R squared law. Now, Einstein thought that there was a unification of those, that having the same force law meant that there was some fundamental unity that existed between the electromagnetic and the gravitational interactions. And he called it the unified field theory. And the last part of his life, he worked hard on that, and nobody's discovered it yet. People are working on it, but nobody's managed to unify. We've unified electricity with magnetism in the 1800s. And then, so now we call it electromagnetism. And we've unified electromagnetism with one of the 2 nuclear forces. So now we actually call it electroweak theory. And we're pretty sure that we've united that with the strong nuclear force, and that's called that's called chromodynamics is what they call it. Anyways, those three forces are unified, but gravity's exceeded, it's escaped unification so far, but people are working on it. So the similarities are inverse R squared law, and it's tempting to think that they're unified. Probably they are, and one day we'll find it out. Maybe one of your grandchildren. So when you're old and gray, Sonny, when I was your age 40 years ago and all that kind of stuff, and your grandchild will, come on, Pops, unification, we got it. It's simple as, cheddar cheese, Well, it won't be quite that simple, but we'll get it eventually, hopefully. Second comment, inverse R squared law. One of the implications that's not mentioned in the book, but I'll give it to you for free. Any force law that depends on the distance, inverse R squared, formally speaking, has an infinite range. So universal gravitation is universal. Your left earlobe is interacting with the Andromeda galaxy, zillions of light years away, and every other galaxy. Now, it's pretty weak. It doesn't, make your ear move or anything. Mainly it's the Earth, because the Earth's so much closer. Same thing with the electromagnetic interaction. Inverse R squared, that's another, and here's another reason. Photons. Photons are massless particles. They are the quantum of the electromagnetic field, and they are massless because the force law is 1 over R squared. We have gravitons for the gravitational field, and they are massless, and they travel at the speed of light. So that's an implication, and it's common for both gravitation and the electromagnetic interaction. The distinction is the following. The electromagnetic interaction can be repulsive. Positive repels positive, negative repels negative. The gravitational interaction is never repulsive. There's no SIGN for mass. There is for charge. And we don't know why that is. Einstein, like I said, we've tried to figure it out. We know that it's there. We don't know why it's there. We hope to figure out the why directly. But in any case, it is a significant thing. The significance of it physically is the electromagnetic interaction can be screened. You cannot screen gravity. And that's why theoretically, you're interacting with every other massive object, every other kilogram and gram of object in the universe gravitationally, but that doesn't mean that you're interacting electromagnetically with everything. If you walk into a metal cage, it's called a Faraday cage, you can't use your cell phone if it's the right kind of cage. And I had a friend that worked for an unnamed outfit that had to do with things that orbit high up in the sky and look down on the Russians. And he had to work inside a room that was lined with copper. And he hated it because it was always sweaty and yucky. But he did that because they didn't want anybody to see anything except for him and his workmates. They didn't want anybody else to see what he was doing with those satellites. I mean, that's all I knew. I didn't know what, just that he was controlling satellites or something. But so that's a Faraday cage. The electromagnetic interaction can be screened because of this distinction. Question over here. Yeah. Screened, S-C-R-E-E-N-E-D. Screened, blocked. Okay. If you're behind a screen, you can't get through. And an easy demonstration of it is just take some wire mesh and form it into a cylinder, and then dip a little transistor radio in there. Turn the radio on so you're getting, WDBO or something like that, and then dip it inside that cylinder, and The radio seems to go off. Bring it back out, and the radio's playing. Put it back in, the radio's, it's not getting a signal, is what's happening. All right, let's go to the document cam. And what we're going to do on the document cam is a couple examples. Good. From the textbook. So let me pause the podcast here. Shh, 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 shh. Okay, we're going to, I'm going to post 2 more talking PDFs on the talking PDF page right after class. But before I do that, I'm going to post the written homework PDF. And this is what it looks like. There's the top half, and it's fairly small type. And it shows you you have 2 protons, and it gives you the location, and you have an electron. And you're going to figure out, you're going to do the net force and the tilt angle, just like we just did, but a slightly different array. And then down at the bottom of the page is a little table, and I'll grade your paper there. Okay, so when we hand it back to you on Monday, you'll be able to look at it and say, okay, I was graded down -1 for F1, but I got F2 okay. All right? So you're dismissed now. It's 10 minutes to 5. I'll post this stuff as soon as possible after class. You're dismissed.